everyone. Thank you so much for joining us today. My name is Victoria, and I'm a Senior Business Development Coordinator at 2H Offshore. We started this webinar series last year in April during COVID lockdown and held a live webinar every 2 weeks in 2020. Going forward, we'll be hosting the events monthly, so we hope you will continue to join us and find the information useful. So with that, I want to welcome you all to our webinar today entitled Delivering Robust, Reliable, and Efficient Pre-Piling Templates for Offshore WTG Jacket Installation. Before we get started, I'd like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we'll go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. Today, we are pleased to share a special webinar with you that is a collaboration between 2H Offshore and our sister company, LDD. From 2H, we have Director Ben Andrew as our speaker, and from LDD, we have Renewables Bid Manager Lee Sked and Engineering Team Leader Simon Studer. So with that, I'd like to introduce our speaker today, Ben Andrew. Ben is a director at 2H with 15 years of specialist engineering experience in design, analysis, and delivery of offshore structures. He has held project management and technical lead roles on projects from concept through to detailed design. He is currently responsible for 2H's growth in fixed offshore wind for our UK office and works closely with our sister company, LDD, on the engineering of drilling and piling templates for offshore wind turbine foundations. So with that, I'm going to pass things over to Ben to get us started today.
Thank you very much for that, Vic. Pleased to be here today to talk on this subject, and I hope you find the content useful. I'll be presenting throughout today, but I've had a lot of support in preparing this from Lee and Simon, so thanks to them for all their support in getting to this point. So over the course of the next 25 minutes or so, I'm going to run through a bit of an introduction into pre-piling templates, some of their key components and functional requirements, what they're for, how they work. But then I'll dive into some details around how we go about designing these things, some of their key features and why they are, how they are. We'll talk a little bit about measurement and controls systems, as they're a really key part of a successful and reliable pre-piling template. We'll talk a bit about deployment and recovery. That's, of course, an important offshore operation to avoid unnecessary delays and costs for the offshore operations. And then we'll touch briefly at the end on a key safety aspect of piling, which is pile run mitigation and how that can be managed. And then I'll just finish with some conclusions at the end, and there should be some time for some questions. So to start at the beginning, when we're talking about offshore wind, there are a large number of potential solutions. On the left-hand side of the screen here, you see the fixed wind solutions, ranging from gravity-based solutions, monopiles, through to tripods and jacket structures on the right there, which is sort of the largest, most fabricated structure for the fixed wind options. We've also, of course, in deeper water and increasingly in the coming years, we're going to see more floating wind applications, first as demonstrators and then into full production systems, where we have a floater with some sort of mooring arrangement to the seabed to tether them in place. But today we're really going to be focusing on only one of these, which is the fixed jacket solution. And I'll explain a little bit about why those are important in the coming years. So first of all, right now, but particularly I think over the next 5+ years, there's a number of challenges emerging for fixed wind, all really related to increasing size and scale. So today's, let's say, standard wind turbine for a fixed wind offshore that people would be planning on, 9.5 megawatts is pretty typical for today. People are planning for 12 to 15 megawatts in the coming years. And there's a pretty big difference in turbine thrust as you move from 9.5 to 14 megawatts, nearly doubling the maximum load at the nacelle. But you factor in on top of that the fact that nacelle is now higher up, And the impact on the overturning moment, which is what drives the design of the foundation, is much more substantial. You're getting more than a factor of 2, maybe 2.5 times the load on the foundation itself. And when you add the increased water depths on top of that, and fixed wind developments are being planned in up to 60 meters water depth. Beyond that, people may be more looking towards floating wind, but certainly up to 60 meters is well within in fixed wind's remit. That further increases that overturning moment. So if you compare a 9.5 megawatt turbine in 20 meters to a 14 megawatt turbine in 60 meters, which might be the norm in 5 years or so, that's a factor of 3 increase in the loading on the foundation. And of course, that means the foundation needs to increase in size accordingly, which brings a whole load of new challenges or increases existing challenges and costs. And that happens across the supply chain, really. It means more fabrication cost in terms of materials, yard capabilities, and the scale of these fabrications. It means more challenges for transportation and lifting, more challenges for the supply chain in just delivering that volume. In-place environmental impact of these larger structures offshore, and maybe particularly importantly, if we think about monopiles, for example, installation environmental impact. Piling the sort of monopiles needed to suit these kind of water depths and turbine size generates an awful lot of noise offshore during that piling operation, and the hammer designs are getting quite extreme as well at that point. Now, the monopile design itself is a very attractive option. They're very compact foundations, relatively, conceptually easy to transport in bulk and lift and install. But they can be particularly susceptible to these challenges, and they keep being pushed to larger water depths and to larger turbine sizes. But it's getting increasingly challenging to deliver on that in an economic way. And that's one of the areas where the jacket foundation really comes in. That the jacket solution does have some benefits here. It has smaller foundation piles because they're on a larger diameter from the turbine center, which may mean they don't have to have the same diameter, wall thickness, or piling depth. And that means you can use smaller hammers in order to drive them, which of course in turn means less noise in terms of volume, although you now have more driving to do. So all of that means they can be more robust to the increased water depth and turbine size, and they can also be more robust to the geotechnical conditions because, again, you're not trying to drive such a massive pile into the seabed. They come with their own challenges, of course, in terms of size and fabrication, but they do have some benefits, particularly as you push into deeper water. So it's that jacket solution, again, that we're really going to be talking about today. So that sort of sets the scene. If we now talk about the actual topic of today, which is the pre-piling template, we need to first of all understand the installation sequence that might typically be used. So step one is that the foundation piles need to be pre-installed. And because we're batch setting a large number of jackets for a wind turbine, it's much more efficient to go and preset all those piles and come along with the jackets later. That's different to a lot of oil and gas operations where a single jacket or a couple of jackets are dropped in and then piled in place subsequently. The jackets then landed over the piles and grouted in place in order to provide the structural connection between the piles and the jacket. And finally, the transition piece and the turbine are installed on the top. So that's the sequence that we want to take. And so the purpose of the pre-piling template is primarily to locate the piles at the locations on the seabed where we need them and to ensure their verticality. That's very important because if they're in the wrong places or they're at too great an angle to the vertical, either the jacket can't be installed at all on top of the piles or the grouting won't be within spec due to sort of lack of annulus or too great an annulus between the outside of the pile and the inside of the jacket sleeve. On top of that, though, they may have a number of other functions that are needed really in order to deliver on those primary functions. We're calling these the secondary functions. So they're going to need some leveling and preloading functionality. That's to ensure the template itself is orientated and positioned and leveled correctly prior to the pile installation. And they're probably going to require some survey and positioning equipment and monitoring to ensure that. So that's some mechanical and some measurement features that are going to be needed. They may also require additional features on a project-specific basis, for example, noise suppression to reduce the acoustic effects of the hammers either locally or at distance. And that could be either HSDs or it could be bubble curtains. Talk a little bit about that in a bit. It may require mud mat breakout mitigation. You don't want to install this thing at the first turbine location, pile 4 lovely piles, and then not be able to lift it out for the second one. So you need to make sure that you can retrieve this thing and reuse it on other sites. And it may even require some level of pile damping, which is something that's been looked at to actually absorb some of the impact that the hammer is putting into the pile. They come with a real range of sizes and shapes and designs, and that's because they need to be built to suit the specific installation method and also the jackets that will subsequently be installed. So typical designs would either be 3 or 4 leg jackets and hence 3 or 4 leg pre-piling templates. And most standard deployment method would be from a floating vessel that installs the pre-piling template and then deploys the piles and the hammers. But designs have been looked at that use a jack-up rig. You can see one of those on the left there, where the pre-piling template's essentially slung below the jack-up vessel. It actually has some sort of sleeves that go around the legs of the jack-up, and then it's deployed to depth from a fixed facility. So there are variations there, but the most typical would be a 3 or 4 leg from a floating vessel. Some things that are being discussed on potential projects in the coming years, as well as options around standardization. Can we standardize the jacket design to allow a pre-piling template to be used on more than one field rather than scrapped at the end of its use? Or could it even be modified or adjusted in some way, either by cutting and welding in additional sections, or in a more active way with sliding sections that allow you to adjust the position of the piles within the piling towers or the overall footprint of the pre-piling template as a whole. And that will help to reduce the amount of material needed to build these things in the first place and increase the speed at which they can be deployed if there can be some level of standardization there. So specific project considerations, which tend to mean these things are custom designed at the moment on a project by project basis. I mean, first of all, of course, the number of piles. Is it a 3 or a 4 leg jacket? But also the dimensions and the weight of those piles. This drives both the slots of the template for handling the piles, but also the loading that's going to go into the pre-piling template during its operation. Choice of hammer, is it an impact hammer? Is it a vibro hammer? Is it both in a sequence in order to preset the piles and then drive them to depth? Template functionality, we talked a little bit around that. What do we actually require the template to do? The control and positioning requirements in terms of tolerances that need to be met. The installation vessel requirements, of course, this thing has to be transported, stored on deck, lifted and installed using the craneage available and the back deck space that's available on the vessel. And so we need to have the right features to suit that particular installation approach. I'll talk a little bit more about that in a bit. Specific installation site regulations and environmental factors. So these may be driven by local sort of government requirements in the region related to the level of noise that can be allowed. That can drive the need for bubble curtains and HSDs, for example. The seabed profile and the properties, so that will affect the level of the amount of leveling that's needed on the individual columns within the structure, but also the design of the mud mats themselves. And you can see on the right there's a design where the geotechnical conditions did not suit a single mud mat for each leg. So 2 different mud mats were deployed on each of the different legs there to spread the load and improve the response. Design life and corrosion requirements, how we're going to mitigate that through painting or CP or other procedural aspects. And how long it's actually going to be used for. Again, if we look to standardize or to make them adjustable for different locations, they may be used for a longer period of time, which will require additional materials and corrosion consideration, but also fatigue performance of the thing during its use. And then again, thinking regionally, particularly capabilities of fabricators in the regions. It's not always appropriate to fabricate in Europe and ship elsewhere around the world, for example. Local fabrication helps with local content, but also cost. and then transportation fleet and access. So we really need to consider all those aspects when establishing the design of a pre-piling template. So here are some of the main features. This is the overall example of just one example of a template. It shows the sort of level of detail. Fundamentally, you've got your pile guide towers, of which there will be 3 or 4 typically in the corners. And then you have a structural frame that's bracing those together and providing the overall rigidity. At the base, you've got mud mats on each corner to support the weight and the operational loads into the geotechnical conditions that are prevalent. And you'll have leveling rams to provide the leveling of the system and maybe the preloading as well. You'll have a pile guide system within the pile guide towers to guide the piles into the seabed in the right location and to support those piles. And then at the top, you'll quite likely have a guide cone to initially guide it into the frame. And this also may be where the HSD, the hydrosound damper, may interface if one of those is required to manage acoustics. And you may have bubble curtains, 1, 2, 3, either local to the frame or global, and maybe wash water systems to help with retrieval. And then you've got the controls and the hydraulics. So these are typically subsea HPUs with controls and umbilicals connecting them to the back of boat for power and supply and controls. And you'll have maintenance walkways and cable routing. Of course, those are not for use when it's in service, but for maintenance when it's on the back of the deck. Sometimes we do use dry HPUs, but I think subsea HPUs are probably used more commonly. So if you look at the pile guide tower in a little bit more detail, you can see that there's essentially 2 levels there where we have rollers. An upper roller that initially is going to dictate, a lower roller that's initially going to dictate the plan position of the pile, and an upper roller which will dictate the pile verticality. And around that, we have bumper frames to prevent damage to those rollers when the pile's being slewed and dropped into place, but also from any dropped objects that may be that may apply in the region from the vessel or from any of the other equipment that's being lifted. So in all cases, these rollers are typically designed to retract out the way when the pile's initially lowered in, so that you don't damage any of those rollers with accidental loading or even worse, damage the pile. Once the pile passes the lower level of rollers, then they can be actuated in order to position the pile, and then the upper ones can be actuated in order to ensure we got the verticality before the pile is dropped through and into the seabed. And you can see here on the right how they are retracted there, either below the bumper frame at the top or below those sort of bumper bars guide frames that sit lower in the tower. So that all ensures that you don't cause any damage to the pile or the rollers when you're running the pile. Below that, we'll have the mud mat. So that mud mat needs to be designed for the seabed conditions. But again, unlike oil and gas, where you're designing a specific structure to go in a specific location, this needs to be used on a number of locations, maybe 60 plus locations on a field, and looking towards the future, maybe on multiple different locations as well. So these mud mats need to be designed for the full range of seabed conditions that you're going to see across your development. And they may even be modular, such that you can have different mud mats for different locations, or you can deploy skirts in specific locations in order to suit whatever variability you may have. If you've got a 4-leg solution, you've also got the option to preload those mud mats. So again, you can use the hydraulics to actuate pairs of mud mats essentially in order to work the soil and preload the soil. That helps to avoid movement or settlement of the frame during operations. If you do get settlement, it's not the end of the world, because the control systems and the hydraulics can re-level the frame during operation, but of course that's not desirable. In addition, even if the frame goes out of level, you can still control the verticality of the piles through the hydraulics on the rollers themselves up to a certain tolerance to allow those piles to stay vertical and located correctly. Key design considerations here, of course, the geotechnical conditions. There may be seabed preparation to work around. Things need to be designed for stability of the overall frame, bearing loads, sliding loads in terms of the geotech. So you may need skirts in some locations. And if you've got, for example, fairly cohesive soils, clays and the like, you may have issues with suction during retrieval as well, in which case you may need wash systems to support with that to make sure you don't damage anything during retrieval. And I've mentioned most of the aspects around the leveling, but it's really important that we get that leveling right, at least to know, not necessarily that the frame is 100% level, but certainly to know what the level is. That provides a datum to work from for the pile verticality. And the system incorporates that leveling function, the mechanics, but also real-time monitoring during the piling operation, and I'll touch on that in a moment as well. So if we now look at the measurements and controls systems that are deployed on it, there's the template positioning itself. That's like any other lift and deployment operation from the vessel. So the achieved tolerances here are really around the capabilities of the vessel itself, using the vessel's positioning systems and a transponder on the template itself. So that would be typically plus or minus a meter, but it's not really a function of the template design. Same applies really to the template's heading, but then when we start looking at its pitch and roll, that is about how the template itself is going to work. And so on the template, we'll have mounted systems such as gyros, altimeters, transponders to know exactly where this thing is, how deep it is, and what its orientation is relative to vertical. Again, the heading tolerance is really around the vessel deployment capabilities. Plus or minus 3 degrees might be typical, but the leveling tolerance is the most important bit here, and we would typically achieve within 1/4 of a degree from the vertical when this thing is deployed. And that can be monitored live throughout the operation. So then the bit that really matters, the ultimate objective of the pre-piling template, is the pile positioning and verticality. So we have the 8 rams typically and guide rollers incorporated within each of the legs. You could maybe have 6 in a triangular arrangement, but we typically use 8. And that's very well known due to having stroke sensors on each one of the rams, pressure sensors on each one of the rams as well, which helps to indicate if we're seeing a potential overload. A thorough dimensional control survey will be done of the frame following fabrication as well to allow that to be accounted for. And then we have inclinometers, lasers, cameras to understand where the piles are and what the overall verticality is. And all of that's fed back in real time through the controls system to the deck. And again, I'll show you that in a moment. So typical pile tolerances, the piles themselves vertical within 1/2 degree, plan position within 50 millimeters, and the top of the pile elevation down to around about 200 millimeters from its target depth. So those would be the typical pile tolerances that we would design for, although in practice you can often achieve better than that. And this shows an example of what the telemetry you get from the monitoring system will look like. So this particular dashboard here is showing in the 4 quadrants. I'll use my mouse to point. In the 4 quadrants here, we have the 4 different towers 1, 2, 3, and 4, and the key metrics against that in terms of its positioning. So this is looking at the template, not the pile, but it's looking at each of those 4 different towers. And then in the middle here, we have the overall heading of the structure as a whole, its overall pitch and roll, and then average responses coming from each of those 4 different columns. And you can see the accuracy that's been achieved on the verticality there, within pretty much 0.1, 0.15 of a degree. Then if we look at the piles themselves, so this is now looking at one of the towers, Tower 4 in particular here. We're showing the rams themselves here, and we're getting the stroke readouts from the lower rams and from the upper rams. And most importantly, we're looking at how this has been positioned relative to the center of the target area. We've also got the distance to go here, measuring the height of the pile above the seabed with a target elevation and the current pile elevation with its follower and hammer above that. This is a snapshot. Above that, we also have it in the time domain showing how they vary with time. So this top one here is showing how the pile is driving gradually deeper as a function of time. And these other ones here are showing how certain parameters such as pitch and roll are, again, varying with time. And then finally, you can get your summary at the end, which is the overall pile locations within the towers in all 4 locations during the operation and at the end. And this is for a particular location on a particular wind farm. And you can see the sort of horizontal separations that are being achieved, within 20 millimeters in this case, well within the 50 millimeter target that we were working to. And that will ensure that the subsequent foundation installation and grouting operation can be achieved in the intended manner. So now moving on to focusing a little bit less around its operation and more around the design and build of the thing. So this can be handled either just as an engineering activity with fabrication by others, or a full turnkey EPC contract. You can deliver them in either way. The most important thing in either case is that there's a really robust interface between the designer and the fabricator to ensure that you realize the design. You're often working on pretty tight schedules to deliver these things. Primary steel might be pinned down early on, but there's a lot of functionality, secondary and tertiary components that will be designed as you go along and need to be delivered to the fabricator and integrated into the fabrication sequence in order to deliver the right solution by the end of the project. So that requires that interface to be really robust and reliable, working almost hand in glove between the engineering contractor and the fabricator, regardless of whether they're under the same contract or not. Key fabrication considerations, increasingly, I think over the next 5 to 10 years, regional considerations are important. Historically, a lot of this work has been done in Europe, but as we look towards growth markets in Asia and in the East Coast US, for example, or even eventually down in Australia, for example, using regionally available materials and regionally available member sizes for fabrication is, of course, going to be important, and using an engineering contractor that understands that regional variation is important to again, easing that fabrication schedule. The fabricator track record, they need to know how to build structures of this kind, where these dimensional tolerances are particularly important, or they need to be coached and supported through that learning process. Quality control is, of course, extremely important to achieve those manufacturing tolerances, as well as the reliability of the system overall. Again, thinking about growth markets, local content is becoming increasingly important. It's not always acceptable to build it in the Netherlands and ship it halfway around the world, even though that may be where you've got the best track record. So you need to trade off that track record and that local content when you're working out where best to fabricate. But those fabricators as well need to be in the right place. They've got to have the right quayside to load out, of course, reasonably close to the installation site. So these are all things that you're going to trade off when choosing your fabricator. Again, whether that's a separate contract or part of a turnkey EPC. In terms of testing and inspection, this goes really throughout the entire supply chain process. Of course, there's the frame fabricator, which has a lot of dimensional control, the usual welding procedures that need to be controlled and inspected correctly to ensure it lasts its design life. But maybe more importantly, you've got all the systems, the controls, the hydraulics, that all have to work together on multiple occasions, on multiple sites across the field. So they need to be really, really reliable. And the way that that's typically achieved is through FATs of the individual components, yes, but also of subsystem assemblies. So quite often we will work with a supplier who's providing quite a lot of the different components that build up the controls and hydraulics, in order that they can test not just those individual cylinders or electrical components, but subsystem assemblies at various different sizes. And increasingly now simulations are also being used to further take that testing to another level, so that you're not just putting in something and seeing what comes out, you're building full simulations around that testing to see how it's going to respond in a real world condition. And then eventually you do move to your SATs, but there may well be SATs on your sub-assemblies once things are installed on the frame before you do your final SAT prior to loadout, onshore or even on the vessel at quayside. And that will continue through the offshore campaign as well, with the maintenance and testing program in between deployment locations. And that's how you achieve the real reliability, is that really thorough end-to-end testing as much as you can in the schedule you have available. Deployment and recovery, these are really optimized to increase workability. You want to be spending as much time as possible with this thing on the seabed and the hammer doing its job, and as little time as possible moving it around. There's an option to wet tow. You don't have to do maintenance operations on these between every single deployment, so they can be wet towed between locations, and that can also help with weather windows, because you're not lowering and raising the thing through the splash zone, which is probably your most restrictive installation stage. To help with this as well, LDD have what they call the Rock Steady connector, which is a single point handling tool that mates with a receptacle. Can be done in different ways. You can either have a permanently fixed bucket, like shown on the top here, or you can have a separate little structure with a mud mat that acts as a lifting aid with the strops permanently fitted to the frame. But either way, this connector stabs in, latches within the bucket, and then lifts the entire structure. And that same component can be used to lift and operate a hammer as well, reducing back deck rigging operations, and again, cutting out some downtime. Umbilical management, so we try and minimize this using the subsea controls and HPUs. That reduces the number and complexity of the umbilicals that are needed. But we will, of course, need reels and chutes in order to deploy those. And exactly how simple or complicated that looks can depend on like the range of water depths you're dealing with across the field, for example, whether you can get away with a fixed length or you need reels. And then finally, pile run mitigation. So this isn't really specifically related to the pre-piling template, but it's an important operational consideration. Pile runs, of course, they do happen, and they can cause damage to equipment, in the worst case, loss of piles, and even worse than that, actually, safety risks to personnel if there's snatch loading on the crane. Sometimes you can't mitigate them. There's nothing you can do. You've got a region of weak soil, and when the shoe of the pile breaks through to that, you will get a pile run. But you can reduce the consequences of them. And our approach to that typically is around, first of all, good quality engineering to predict when they're going to occur. So that's based on your survey data and boreholes, and geotechnical engineering to understand when it might happen. You can deploy pile driving analyzers offshore as well to help spot an impending pile run. You generally see stresses reduce as you approach the region of weaker soils, and you can back off on hammer energy or blow speed in order to reduce the impact. And then there are systems out there like the Crane Master system, which is shown on the right there, which can help at least to absorb the shock load. So that at least mitigates your safety concerns and your damage to equipment concerns, although you could still lose a pile through that. The final option is a pile catcher system. These can either be deployed on the vessel or potentially deployed subsea. But these can be quite complicated to engineer. And you still need to figure out what you're going to do once you've caught the pile, because if you let go of it, it may well just carry on again. These, I think, are more important when the piles are being fabricated offshore, so where they're being made up out of joints offshore, and losing it subsea may mean you then suddenly can't attach the next joint. For wind turbines, jacket structures, that's not normally the case. The piles are normally prefabricated, and the risk of a full pile loss is very slim. So generally speaking, we would approach this through an operational approach rather than through a catcher system on the pre-piling template, but it's potentially possible. So to conclude on all that then, before we move to questions, well-designed pre-piling templates fundamentally are there to ensure efficient piling operations, and that those operations are robust and reliable, minimizing downtime, and ultimately to make sure that those piles end up in the right places and with the right verticality to support the subsequent foundations and grouting operations. In order to deliver on that, the designer really needs an integrated understanding, and I think that's the really key point here, is the phrase integrated understanding of the control system, specification, design and operations, of the offshore operations themselves, so that's the piling and the handling operations around that. Of course, the structural design of the frame, the mechanical design of the components, and the geotechnical design of the seabed interface, and also the local fabricator operations and supply chain. If you particularly if you're looking at designing a pre-piling template for a growth region. So that concludes my presentation content for the day. Vic, I don't know if we have any questions.
Yes, we do. Thank you so much for all the information. If anyone has any more questions, go ahead and send them in, and I'll just get started asking these ones. Okay, first question is, what is the maximum pile size that can be accommodated?
Okay, so typically, I think pile sizes for these systems would be in the sort of 2.5 to maybe 3.5 meter range. There's no specific limit here. I mean, these piles are already considerably smaller than monopiles, so driving them's not an issue. The challenges will mainly be around the scale of the overall structure that you end up with there, and in sizing the rollers for the higher loads. But we're not really at the limit of any of those components yet. I think probably back deck space and so on is more likely to drive before that. So yeah, 2.5 to 3.5 certainly, but that's not a firm limit.
Okay, perfect. The next question is, can multiple skirt piles be accommodated?
So yes, I'm not aware of any for which that's been done to date, but it's quite a standard solution in oil and gas jackets to have multiple smaller piles. I think the advantages of that, of course, if you've got smaller piles, again, it's like the difference between a monopile and a jacket. You can potentially use a smaller hammer in that case to pile it to the required depth. You may not need to pile as deep either, because you've just got more piles resisting the overturning loads. In terms of the pre-piling template, you're getting more congestion there, having rollers that need to fit in around each other. Maybe that's where you'd move to 3 instead of 4 rollers to give yourself a little bit more space. But again, in principle, there's no issues with doing that and having more skirt piles rather than just the same number of piles as you have legs, essentially.
Okay, thank you. The next question is, it's kind of a two-part question. How is the mechanism of grouting between pile and template? And is there any grouting in between the pile and the soil?
So in this case, firstly, in terms of grouting with the soil, no. So this is a piling template. So all we're doing here is hammering the pile itself into the seabed. It's building up skin friction between the pile and the soil, and that's giving you your actual resistance, your pull out and your push in resistance that reacts to the overturning moment from the turbine and the foundation itself. So there's no grouting there between the pile and the surrounding geotech, essentially. Just as a little bit of an aside, there is, of course, an option to drill and grout foundations, and some geotechnical conditions will be more suited to that, particularly if you're dealing with particularly hard rock, limestones, or volcanic rocks, potentially, where you actually want to drill a socket and grout the pile in place. So that's absolutely a possibility, but it's not what we're talking about specifically today. Then in terms of grouting, what you'd normally have is you're going to have a stick up of the pile above the seabed, or piles above the seabed. The jacket will be lowered down over that. And then normally what you've got is the sleeves of the jacket will have some grout seals around them, maybe 1 or 2, back up in a primary grout seal, depending on the column of grout that you're supporting. And that will then be grouted in place using a stinger or whatever to form the bond between the preset pile and the jacket sleeve. As I mentioned earlier on, this presentation is in partnership with LDD. They've got a good degree of expertise in, their main business is drilling foundations. These pre-piling templates are just one of their other product offerings, but they also now incorporate Core Grout, which is another one of our sister companies within Action that get very heavily involved in specifying and delivering the grout and the grouting systems for these kind of applications. Lee, I know you're on the line there. Is there anything you want to add on the grouting?
No, I think you covered it there. I think we're looking. The question was really more suited for that sort of drilled and grouted solution. What we're talking about today is a driven pile, and as you rightly said, the template is then lifted out over the top of these piles, and the jacket is landed over the top and then grouted. That's the secret.
Thanks, Lee. And I mean, to the person who asked that question as well, if you'd like more information, outside of this about drilled operations, grouting operations, reach out either to myself or to Lee, and we can point you in the right direction for that.
Okay, thanks, guys. Next question. What soil conditions are appropriate for these systems?
Okay, so I think the soil conditions, the question's more around the piles again than the pre-piling template, which is fine. I mean, the piles work best, driven piles work best when you're dealing with clay soils. They give you good axial capacity, but they're also relatively easy to pile into. That doesn't mean you can't pile in sandy conditions, of course, and even in certain rock conditions, you can pile in as well. But for once you've established the drivability of the piles themselves, the depth that you can achieve is what you need to build up the axial capacity. In terms of the pre-piling template, it's just around the mud mat design itself, and you can design those for sands, for clays, for rock conditions even. It's just going to affect whether you've got skirts, whether you haven't, how large and bulky those mud mats are. Maybe you need 2 instead of 1, as I showed earlier. Maybe you need wash systems if you've got this very sort of high cohesion layers of clay, for example, in order to remove breakout loads. But yeah, the pre-piling template itself, it can handle most soil conditions. Probably the biggest issue actually might be slope. So you can handle a level of slope with the pre-piling templates, but there's going to be a limit there. Lee, anything to add on that one?
I was just going to add, if you've got a variety of different conditions across the site,
Sorry, Ben, could you mute while Lee talks?
Yeah, I was just going to say, if you've got a variety of different conditions across the site, we don't have to have just one design of mud mat. So if you've got rocky conditions in one location and soft in the other, we can actually design modular mud mats, which would allow you then to add on or take away certain elements of those mud mats for those specific locations. So we can look at the site as a whole and try and optimize for one, let's say, average mud mat design, or we can look at it to sort of optimize the design if required. So it's possible for all conditions, and really, as Ben pointed out, the soil conditions are really purely for the interface with the template is the mud mats. So.
Thank you, guys. Great, thank you, guys. Okay, I think we have time for one more question. What is the typical environment condition for template deployment and driven pile installation?
I think that might be a better one for Lee. Do you have the answer on that one, Lee?
I would say it varies. I mean, depending on the size of the pile, the weight, the length, the diameter, that will drive your PPT design, and then subject to the return period that is designed for will dictate the size of the structure. Yeah, we typically look at that on a project by project basis. It's very hard. Obviously, we seek to have the largest operable window we can. However, there's a payoff between being able to cope with, say, a 50-year storm compared to a 1-year return. So we look for the sweet spot in between, and then we advise the operations around that. And this it depends which area you're in. If you're in a North Sea, which is relatively sheltered compared to, say, offshore Taiwan, where it's you get a lot more higher energy systems coming through. So.
Thanks, Lee. Yeah, that was pretty much going to be my answer. I wondered if you might have something more specific, but that's fine. Yeah, I think it's right to say it varies. In particularly severe environments, well, not necessarily storm conditions, but where the day-to-day weather is not so nice. That's where the subsea tow option, I think, can come in quite useful as well. That you're not having to deploy it and retrieve it through the splash zone. So if your vessel can do the operations, then you can move the pre-piling a template around subsea. Okay, any other questions, Vic?
Okay. I think that is it for today. I think we're out of time. So thank you so much, Ben and Lee, for all the information on the topic that you gave us. And like I said, sorry, if you think of any more questions in the meantime or you'd like to continue this discussion, you can contact Ben or Lee directly using the details provided here. And I want to thank our audience for your time and participation. We hope you all found this useful and will join us for more webinars in this series happening at the end of each month. Our next webinar will be on June 23rd on challenges in HPHT riser technology. So you can check out the 2H website and LinkedIn for more details and to sign up. Again, please look out for the recording of this webinar in your email in the next 24 hours, and we hope you all enjoy the rest of your day. Thank you so much.
Thank you, Vic. Thank you, everybody.
Thank you, Ben. Thanks, everyone.